Okay. All right, so here we have Henry's law constant for the solubility of helium gas. Henry's law is just, or I guess I'll just go through the questions. So this is my third one. So we have a Henry's law constant, which I'm going to call KH, is 3.8 times 10 to the minus 4 molar per atmosphere. And it wants the value in terms of millimeters of mercury. So to do that, we just need that 1 atmosphere is 760 millimeters of mercury, or 760 torr. So then our KH is 3.8 times 10 to the minus 4 molar per atmosphere times 1 atmosphere per 760 millimeters of mercury. So the atmospheres cancel. And we now are just dividing 3.8 times 10 to the minus 4 by 760, which comes out to be 5.0 times 10 to the minus 7 molar per millimeters of mercury. Okay, so now the second part of the question just asks to calculate the concentration. So Henry's law relates the concentration of dissolved species to the Henry's law concentration, or Henry's law constant, and the partial pressure of the gas. And so part B says if our partial pressure is 293 millimeters mercury, what is the concentration of dissolved species? So for this, we just need to simply go through this equation. So our concentration will be 5.0 times 10 to the minus 7 molar per millimeters mercury, multiplied by the partial pressure, which comes out to be 1.465 times 10 to the minus 4 molar. Okay, and then part C asks what volume, what gas volume of helium is dissolved in 10 liters of water at this temperature and this partial pressure. So this is our molar amount, and recall that this is moles per liter. So if we have 10 liters of water, then we have the number of moles of helium is 1.465 times 10 to the minus 4 molar times 10 liters, or 1.465 times 10 to the minus 3 moles. Forgot here that I probably, well, that's a constant, so I think that's probably okay for significant figures, probably 1.47. Okay, so there's our number of moles of helium which are dissolved in our 10 liters of water. So now to get our volume of gas, we need to use the ideal gas law, so PV equals nRT, solving for volume here. So volume is just nRT over P. And P in this case will just be our partial pressure. So N is this number of moles. R is our universal gas constant, which is 8.314 kilopascal liters per mole Kelvin. So that's the value that I always remember. So we're going to have to multiply this by our conversion to millimeters mercury, which is 760 per 101.325 kPa. So the kPa will cancel, and we'll actually get an R of 62.36 millimeters mercury liters per mole Kelvin. Our temperature is given in the question as 25 degrees Celsius, which we're going to have to convert again. So that's 273.15 plus 25 Kelvin, which equals 298.15 Kelvin. So there's our temperature, our R, we have our N, and we're given in the question that our pressure is 293 millimeters mercury. So now combining all this into our volume expression, we have that volume is 1.465 times 10 to the minus 3 moles times our gas constant, which is 62.36 millimeters mercury liters over mole Kelvin, times our temperature, which is 298.15 Kelvin, and divided by our pressure, which is 293 millimeters mercury. And we can quickly do a check on our units to make sure we didn't make any mistakes. And everything cancels, giving us liters, which is a volume, so that's good. And if we run this all through on our calculator, we get 0.09296 liters, which equals 92.96 milliliters. I ran it to 4 significant figures, but I don't know why. Because I believe in the question, I guess it gets tricky. Yeah. Okay, so that's our volume of helium gas, which is dissolved in 10 liters of water at that temperature and with that partial pressure. Okay, so let's go through the solutions. So first of all, might as well go up to the top here. So so we get about 5 times 10 to the minus 7, so that looks good. Our concentration is just by running through that, so 1.47 times 10 to the minus 4, so that looks good. And then running through this, we're going to use ideal gas. Which is about, which gives us 0.0933 liters, or about 93 mils. So it looks good. That would be just a different, and in rounding there, so solution is correct.